Swayam Prabha. Digital India. Educated India.
We continue with the discussion on module 9. In our previous lecture, we were discussing some aspects of the Linux operating system. We continue with that. Now, the first thing that we discuss in this lecture today is regarding memory allocation. Now, before we go into this, let us understand something. Here, as you can see, it uses something called the buddy algorithm. But before that, let us look into what we had discussed earlier regarding memory management. We saw that we have virtual memory, where the physical memory is divided into page frames. The user processes the virtual address space also divided into pages, and the pages are mapping into page frames. So, whenever a process requires a page, it is allocated a page frame. Now, typically the size of a page frame is fixed. Now, what has been found is that if we use a fixed page frame size, the efficiency of memory management may not be that high, because some processes may require less memory, some processes may be requiring large memory. So, process which is requiring, let us say, which is requiring 500 kilobytes of space, but you are giving it 2 kilobyte at a time. So, it will be needing 250 pages. So, one by one it has to allocate. But if you can allocate all 500 pages at the same time, then you know that this is the requirement, you are given it at the same time, and the process can run more efficiently. Now, the concept of this buddy algorithm, which is used in Linux, is based on this motivation. Here the concept, let me first try to explain. Suppose I have a memory space available with me. This is my total memory space. Certain space is there, and obviously because memory address is in binary, the total space is some power of 2. Let us say 2 to the power some power 2 to the power k. So, whenever a process requests for some memory, it tries to divide this, like you first divide it into half. So, each of the half will be 2 to the power k minus 1 and 2 to the power k minus 1. Suppose the requested size is even less. So, you again divide this into half, again divide this into half, and finally, you can possibly allocate this. And when you are dividing a larger space into two halves of equal size, they are called buddies. So, the buddy algorithm comes from this concept, that you are dividing a space into two buddies, and one of the buddy you can again divide into two buddies, and so on. So, when you are allocating space, like in this diagram which I am showing on top, suppose initially this space, the size of this block was 128, 2 to the power 7. But your request is for 2 to the power 32, or means for 32, 32 means 2 to the power 5. So, 120 is divided into two buddies, 64 and 64, and one of the 64 is further divided into two buddies, 32 and 32, and one of the 32 you can allocate. So, for allocation, the first thing is that when a process is allocating some space, it is not allowed to allocate any arbitrary value. That means, I need so many bytes, it must be some power of 2. Like for example, if it requires 56 bytes of space, so it will say that, well, I need 64 bytes, which is a power of 2. So, now the memory management unit will search through this buddy list, that if a block with that exact size is available somewhere, if that exact block is available, you allocate it straight away. But if that exact block size is not available, then you have to go for a higher size block, like I have shown here, split it up into two halves, possibly again split it up into further halves, and return the largest enough buddy that can fit this request. So, until you get the 64 bytes, you go on partitioning, that way you allocate. And after a process is finished using that memory, it will be returning it back, that is deallocation. Now, in deallocation, whatever the allocated segment was, some power of 2, that will be returning to the free list. Now, after returning, if you see that if two adjacent buddies are both free, you combine them together into a bigger segment. So, buddies get combined. During allocation, buddies might get split into smaller buddies. This is how the buddy algorithm works. I am showing a more elaborate example here. Let us suppose I have a 1 megabyte block, 1 meg, and 1 meg means 2 to the power 20. Let us say in the sequence of time I am showing, there is a request for size 100K. So, what is the nearest power of 2? 100K, just 128K. 128K is the nearest power of 2. So, 1 meg will be divided into 512 and 512. 512 will be divided into 256, 256. One of the 256 will be divided into 128, 128, and you get that 128. After this partitioning, you see this request, suppose we call it A, this A is allocated 128K, and now these smaller free spaces are 128K, 256K and 512K. There are now 3 smaller free segments available. Next, let us say there is a request for 240K. So, what is the next higher power of 2? 256K. Search the buddy list, free space list, and see if a segment of the exact size is available. Yes, there is a 256K available. You allocate this request to 256K, call it B. So, at this point, 2 of these segments are allocated, this A and B, and there is one free space 128K, one free space 512K. Okay. Next, there is a request for 64K coming. 64K is already power of 2, fine. You find which is, how to allocate. You find that you have a segment of 128K, but your request is 64K. So, divide 128K into 2 parts, and one of the part you allocate, call it C, and already A is allocated, already B is allocated. So, now with respect to free space, you have one small 64K and one larger 512K. These are 2 free segments available. Next, let us say there is a request for 256K again. This is also a power of 2. So, you see that this 64K which is there, this is not enough. You will have to go to 512K, divide it up into 2 half. So, one half you allocate, other half remains free, and on the other side this 64K is also free, and A, B, C, D, all 4 blocks are occupied. This is A, this is C, and this is B. Suppose now B has finished. So, B you want to release. So, B had occupied this 256K. So, B is releasing. So, now our free space is this, this and this, 64K, 256K and 256K, but none of them are buddies. Side by side if they are, you can combine them. 2 blocks of the same size side by side, you can combine them. Okay. Next, let us say A has finished. So, A is also releasing 128K. So, now your free space is 128K, 64K, 256K and again 256K here. Now, some other process is requesting another 75K. 75 is not a power of 2. So, the next higher power is 128K. So, it will be allocated 128K. So, already the first 128K is available block. So, you allocate this, call it E. So, now the free blocks are 64K, 256K and 256K. Others are allocated, E is allocated, C is allocated and D is allocated here. Now, let us say C has finished, C will be releasing it. See, after releasing C, what happened? Let us see. C was here, right? C was 64K, the right 64K was already free. So, two 64K free will come side by side, they will combine together and a large 128K body will come out as free space. So, now you have 128K, 256K and 256K, these are 3 free blocks. Let us say E is releasing now. So, this was E. So, if E releases, this 128K and 128K will be side by side, merge them, it will become 256 and that 256 and another 256 are again side by side, merge them, you get a single 512K free space now, and on the right side you have 256K. Finally, when D is released, this D and this 256K will merge together 512 and that 512 and this 512 will merge together, that will be again 1 mega. So, like this allocation and deallocation goes on in the buddy algorithm. Okay? Fine. Now, talking about the Linux file system, there are some important directories. So, the Linux directory starts with the root, root is denoted by a /. Under root there are a number of folders. Some of the very commonly used folders are bin, these are shown, dev, etc, lib and usr. Under this there may be more folders and subfolders. Okay? But what is the main purpose of these 5? These are very important ones. There are many more. Bin is a short form for binary, and by binary we sometimes mean executable programs. All the executable programs, utilities, like see in Linux already I said you have commands like ls, cat, copy, these are all utilities which are present as executable programs. When you type cp, that executable program cp gets executed. So, all these programs are stored under the bin directory. Okay? And secondly, I said that in Linux or Unix also, all IO devices are treated as files. Okay? And corresponding to each IO device type, there is a device driver program. That device driver program handles all IO requests. Under this dev folder, all these IO device driver files are stored. Like you can have under dev, you can have one TTY01, you can have one CD-ROM, there are many. So, all different kinds of IO device types are there, they will be under dev, there will be one file for those. Under etc, you can have a number of miscellaneous commands, miscellaneous programs, they will be all stored under etc. And many a time we need library files, these are stored from lib. Library files are used for compiling programs which use some system utilities which are present in that library. And lastly, whenever new user accounts are created in the system, as you know, when you use a Linux operating system, the first step is that you have to create an account for yourself, then you log into it. So, in a system there may be accounts for 10, 100,000 users. So, for each user there is something called the home directory. So, under this USR, there will be one directory for me, let us say I call it ISG, there is one directory for someone else, let us call it Amit, and so on. So, for every user there will be a folder created under USR, which is the home directory. Under that means whatever that user wants can create folders and subfolders, that is up to that user. So, these are some of the essential directories that we see at the highest level under the root. Okay. Of course, there are more, there are many others under root, but these are the most important ones. Okay. There are two very important commands. So, we talked about files, we talked about copying files, moving files, renaming files, but there is something called linking a file, mounting a file. So, what is the meaning? Suppose I have a folder, let us call it XYZ. I have another folder, I call it ABC. Under XYZ, I have a file whose name is a.txt. What I can do, under the ABC folder also I need that same file. So, I can do it in two ways. I can either copy that a.txt into this folder ABC. If I do copy, then this new file will also be occupying space in memory, in disk. So, double space will be required, or alternatively I can create a link. I can create something called a link, and I can give any other name, not necessarily a.txt same name. I can give, let us say, b.t. But when I access this b.t file, it is actually nothing but that a.txt same file. So, we are not storing any separate thing for b.t, it is just providing a link that b.t is actually that a.txt. This is called linking a file. So, we can link a file which is stored in one directory to another file in some other directory. You can use the same name, or as this example shows, we can use a different name, and the command to do it is called link. Link, you give the original file name which is already present. Tilde means home directory. Home directory, under that home directory there is a folder docs, under docs there is a file myreport.doc, that I want to link to my present directory. Well, here I am using the same name, not the same name, different name, I call it new dash report. So, in my current working directory a link will be created. That link is nothing but that myreport.doc, but now I will be accessing it with a new name, new report.doc. There is another command called mount, this I shall be explaining a little later. Like you see, when you are using a file system, you know there are folders and subfolders. So, just now I said there is a root, under root there are so many other directories. Suppose I insert a CD-ROM into the system. Inside the CD-ROM there is a separate file system, that file system I am inserting. But after inserting, how do I use it? What I do, this entire CD-ROM I mount somewhere in my existing file system, and I can give it some name. For example, in this example I have shown, I give it a name official. So, this dev CD-ROM, this is the device driver for CD-ROM, that gets mounted at /official. Mounted means what? Whenever I now want to access a file in the CD-ROM, I will have to access it at /official / whatever after that, because everything will be under that official. This you can do using the mount command. Okay. Well, some examples are shown here. This is the example of link, another example is shown. Suppose under user there is one user called Fred, another user called Lisa under the user directory. Under Fred there are 3 files A, B, C, under Lisa there are 3 files X, Y, Z. Now, what I can do, under Fred I can create a link. Well, here I am showing the same name, I am not changing the name, I am linking to the file x. So, x will also appear here. If you do a directory listing under Fred, you can also see x, but you will see it as a linked file. There will be a L displayed in the file type. L means it is a linked file. Okay. So, now essentially this Fred folder will contain 4 files, but one of them is actually a link file which is stored somewhere else. Okay. Similarly, when we talk about mounting, let us say this is an existing file system which is there on hard disk. I have booted or started an operating system. This file system is already there. As you can see, under slash there are 2 directories A and B. Under A there is a directory C, there is a directory D, and there are files PQR under them. Now, I insert a floppy disk or a pen drive or a CD-ROM something. Now, inside a pen drive which is formatted under Linux, there is also a file system. Inside a CD-ROM there is a file system. Inside a floppy disk there is also a file system. So, whatever I insert, that itself is a separate file system, and using mount I can connect or I can join this file system anywhere I want in my existing directory structure. Suppose I want to mount it at B, so it will get mounted under B, this XYZ will come under B. So, after mounting, as if my file system will look like this. Many a time, whenever a computer system has multiple disks, multiple hard disks, at the time of booting all those disks get mounted and they are joined in different places, and whatever you see in the directory structure is the integrated view with all the mounted file systems together. Okay. This is how it works, and when you are done, there is another command called unmount, umount. I have not gone into that. You can unmount it again. Now, talking about using files, file systems, there are again a list of file system commands or system calls which you can use. Some of them are shown here, there are several modes, and these are low level commands, not the commands that you use in a high level program when you are writing a C program. Not in a C program, you can also call the low level function calls by calling the system library. These are the system library functions. There is a function called create. You can create a new file. You can create a file with a name. You can tell the mode, what mode you want to create in, read only, read write, write only, whatever. Then there is a system call called open. So, you are opening a file, and again here you specify what kind of access permission you want to give, and create an open system call that returns a file descriptor, and when you are done with that file, you can close the file where you specify that same file descriptor. For accessing the file, you can read or write. There are 2 functions here, one is a read, other is a write. Now, in both this function call, you specify the file descriptor, you specify a buffer space in memory, you specify a pointer to a memory location. That means, you create an array or a block of data, you specify a pointer here, address of a memory location, and how many bytes you want to transfer. These are low level read and write calls, not scanf or printf that you do in C. Similarly, for write, okay, and it returns the actual number of bytes that were read or written. And I mentioned for a random access file, you can directly put your read write pointer anywhere in the file you want using a command called seek. So, at the low level there is a function called lseek, where you can specify an offset, that where you want to set the pointers. And there is a third parameter called whence. It tells you that offset you are specifying, is it an offset from the beginning, is it an offset from the end, or is it an offset from the current file pointer. So, you can specify that how you are specifying the offset. Then you can get the status information about the file using two commands, stat and fstat. Two versions are available. Then this pipe you have already seen, you can create a pipe, and you can set some options in the file by using the f control CNTL command. So, you can lock a file. Suppose you want to access a file, but before that you are locking the file so that no one else will be able to use it. That is also possible. So, there are several options available here. So, these are lower level system calls, and if you want to use them, you must know exactly how the system calls work. Okay? And just like files, you also have a directory. Now, here you understand one thing, in Linux a directory is also a file. A directory is stored just like a file, but the contents of the files are different. Okay. That I will come a little later, but before that there are a set of system calls available to manipulate the directory, right. Firstly, these commands already I have mentioned, make directory and remove directory. You can create a new directory by calling the make directory command. You can specify the name of the directory name with path. You can also specify the mode, what kind of access permission you want to give to the directory. And when you want to remove the directory, you can specify a path, which directory you want to remove. Okay. And I have already shown earlier that there is a command in Linux called link, using which you can link a file to the other. You can do it at the command line by typing, or even in a program you can call this system call to create a link. There is a system call, a function called link, you can call this also. First you specify your existing file, the path name of the existing file, and the path name of the link you want to create. So, the link will get automatically created, and after you have used the file, you do not want that link anymore. You want to you do not want to delete the original file, but you want to delete the link. The command is unlink. You call a function called unlink, specify the path name, whatever link was established at that point, that link will be deleted. To change the working directory, this also we have discussed earlier, you can call this chdir function. So, you can use these commands in the command line mode on the terminal, or you can call them as functions from a C program, right. As I said, a directory is nothing but a file. You can open the directory file and start reading from there. You can also do that. To open a directory, there is a special open command called opendir. Similarly, when you are done, you will have to close the file. For directory, the command is close dir. These functions you will have to call to open a directory and close the directory. Similarly, for reading the entries in a directory, there is also a function called read directory. Typically, every entry in the directory in Linux consists of two things. One is some name, another value, this we will talk about a little later, some kind of an index. There are two things that are stored in the directory. This index actually specifies the value of the something called an inode, index node, where all the details about the file is stored. Okay. And after you have read the directory, suppose you want to again start reading from the beginning, then you can call a function called rewind directory. So, it will be rewinded from the beginning, and all these functions you have to give dir as a parameter, where dir was returned by this open dir, the directory identifier. Okay. Fine. Now, talking about file system, we mentioned that there are a large number of different types of file systems. In Linux, one of the popular classes of file system are the ext file systems, ext2, ext3, ext4, various versions are there. So, very briefly, here you look at the ext2 file system, how it broadly looks like. Now, in the disk, you know that there are sectors, there are blocks, the way they are stored. So, basically in the disk, in the beginning, you have a block which is called the boot block. Whenever you turn on a machine, there is a default hard disk from where you are supposed to boot. So, what happens in booting? There is some code which is there on the ROM on the motherboard that runs first, and that code loads this boot block from the disk. That boot block contains a program, that program starts running, and once that program starts running, it will bring up the file system, all the other necessary things will also be loaded, and now the file system will be ready to use. And after the boot, there may be a number of, here it is mentioned as block groups, but these block groups are very similar to what we call as partitions. So, a disk we can divide into a number of partitions. In each partition we can have a file system. So, you can say one file system per partition. In this case, block group that you are saying, that is nothing but a partition. Now, what is there inside each block group? That means a file system. How it looks like? Inside a file system in Linux, you can see there is also a structure here. The first one is very important, is something called super block. Super block contains all information about the file system. What do you mean by all information? What is the size of the file system? What are the total number of blocks? What are the total number of occupied and free blocks at this point in time? Total how many files can be created? There is something called index node on inodes. Every file corresponds to an inode. If there is space to store 1000 inodes, that means you can create a total of 1000 files max, not more than that. So, super block contains all this information about the file systems. Then for this partition or the file system, there are some further information, group descriptors, you store some additional information about this, and as I said, you need to have information about some free space. Free space here is maintained by a bitmap which is stored here. Free blocks, information about free blocks are maintained in a bitmap like this. And as I said, every file is mapped to an index node. Index node in short is called a inode. Inodes are stored in the disk as part of the file system. There is a fixed space where inodes are stored here. The amount of space that you give here, that will determine maximum how many inodes are possible. And how many of these inodes are currently used, how many of these inodes are currently free, that is specified by another bitmap. And the actual data block says. So, basically block bitmap will contain free space out here, and inode bitmap will contain free space out here. So, here this file system contains information about everything. So, again I am not going into the details of each of these fields. Well, inodes is interesting, I shall discuss inode in some detail, but this is how it is laid out. Now, inside this ex2 file system, a small example. Here I am showing a directory. Directory is also a file, right? I said directory is also stored as a file. So, I am showing in that file what are the things that are stored. This F indicates it is a regular file. 8 indicates how many characters are there in the file name, and this is the name of your file, 8 characters. Right. This is your second file, and there is a pointer out here. This is there is a pointer which points to the next entry of the directory. In the next entry of the directory, you have again some information. This is also a regular file. There are 10 characters in the file name. The file name I have given as voluminous. There are 10 characters. Similarly, there is a pointer to the next file, which is this. Here the file type says D. D means this is a directory file. There can be subdirectories under a directory, and the name, there are 6 characters, the name is big dir, and this part is unused. So, this pointer is pointing to null. So, this is null. So, there is no more. Right. Now, every of these files contain an inode number. The first file contains inode number 19, that means this colossal is stored in inode number 19. Voluminous also inode number 19, because this is a directory file, but this is a separate directory big dir, this has a separate inode number 88. Now, suppose you have deleted voluminous. So, now it will look like this, the central part will be unused, and this pointer is directly pointing to this 88. So, this is basically how pictorially it looks like. All right. Now, let us come to inode, index node. Index node keeps track of the file data. In addition, it keeps track of some information about the file. So, it is basically some kind of a data structure that keeps track of the files, and the directories is also like a file. I said it keeps track of all files and directories in Linux. So, every file or directory you create, it is associated with a unique inode. It has a unique number. As I said, what does a inode contain? It keeps track of various file attributes. We shall show what are the kinds of attributes that are there in inode, as well as where in disk the actual file data is located. So, we shall see that where in disk some pointers, there are different kinds of pointers called direct pointers, single indirect, double indirect, and triple indirect pointers. This we shall see. In a directory, when you store a directory, you have the file name, as we have seen just now in ext, you have the file name, and also you will be storing the inode number. Nothing else is required, because inode number contains all information about the file. Okay. Let us see some of the fields in the inode in the ex2 file system. There is a field called mode. You see number of bytes is also mentioned, which field is what size. This contains the file type, whether it is a regular file, whether it is a device file, an IO device, whether it is a linked file and so on. Protection bit, what kind of access rights are there, who is the user of that file, group, set user, set UID, user ID, group ID, GID, these are also there. Number of links, if this file is linked to some place, how many links are there, it keeps track of the number of links. And who is the file owner, UID, which is the group of the owner, group ID, total size of the file in bytes. So, see, this will give you a restriction. 4 bytes means 32 bits. So, the total file size can be maximum 2 to the power 32 bytes, which is about 4 GB, 4 gigabytes. But if you want files of even larger sizes, you cannot do it in ext2, you will have to go for a higher version, ext4 or something. Okay. Then there is a, these are the, this ADDR contains pointer to the disk blocks where the data are located. This we shall see, there are total of 15 pointers, 12 disk blocks and 3 indirect blocks, 15 pointers, each pointer containing 4 bytes. So, total 60 bytes. Generation number I am not going into detail of this because we have not discussed all these things. So, it keeps tracks of how many times an inode has been used and some times. What is the last time the file was accessed, last time file was modified and last time the inode was changed. So, all these things are present in the inode. And inside the inode, and see here I said that ADDR contains 15 pointers. So, here specifically I am looking at the ADDR. So, here are the 15 pointers. First 12 of these pointers are direct pointers, they directly contain block numbers of the disk. So, they directly point to disk block numbers. The 13th entry, that is a single indirect pointer, that means they point to disk blocks and these disk blocks contain some disk pointers. So, from there they point to data blocks. And entry number 14 is double indirect. Double indirect means there is an indirect block which contains pointers, they point to some blocks, many blocks, they are also indirect blocks, they also contain pointers, and then finally you have the disk blocks. So, you see, if a disk block, let us take an example, if a disk block can hold k number of disk pointers, then a single indirect block can store information about k disk blocks. Double indirect can hold information about k square disk block, because for every this k there is another k, k plus k plus k plus k, it becomes k square. And triple indirect, there is another level, indirect, that become k cube. So, for smaller file sizes you may not need 13, 14, 15, but when files are larger you may have to use this multiple levels of indirect blocks. Okay. Let us work out a small example. Suppose I have a block size of 4 kilobytes, and to specify the block number, let us say we need 4 bytes as in the example also. So, in a block size of 4 bytes, how many pointers we can store? The block size divided by the block address. So, we can store 1k block pointers per block. So, there are 12 direct pointers, right. So, in 12 direct pointers, total how much space disk area I can address? There are 12 direct pointers multiplied by each block can hold 4 kilobytes, 4 KB. So, it comes to 48 kilobytes. So, if your file size is less than or equal to 48 kilobytes, then the direct pointers are sufficient. Now, let us come to indirect pointers, single indirect pointers first. So, it contains the address of a block and that block contains 1024 further pointers. So, it is pointing to 1024 blocks. So, there is only one such. So, it will be 1024 multiplied by 4 kb. See, 1024 means 1 k, right. So, 1 k multiplied by 4 kb means it comes to 4 MB megabyte. Double indirect pointer, I said total number of pointers how many? 1024 whole square, because 1024 pointers in the next table, each of the pointers are containing 1024 pointers again, 1024, 1024, 1024. So, 1024 whole square. So, using double indirect pointers, it will be 1024 whole square multiplied by 4 kb. So, 1024 is 1 k. So, 1 k whole square means 1 meg, 1 meg into 4 gigabyte how much? 2 to the power 1024 whole square is how much? 1024 whole square is 2 to the power 20, because 1 k means 2 to the power 10. You multiplied by 4 kilobyte, 2 to the power 20 is nothing but meg, right, mega. 4 kilobyte, it becomes 4 gigabytes GB. And capacity using triple indirect pointers, it will be 1024 whole cube into 4 kb. 1024 whole cube means what? 1 k into 1 k into 1 k, that means it is 1 gig. That means 1 gig multiplied by 4 kilobyte. Gig multiplied by k means tera, 1000 giga. So, this comes to 4 terabytes. See, these values are negligible as compared to 4 terabytes. So, you can say your total disk capacity will be 4 terabytes. Using index structure like this, you can address maximum disk space of 4 terabytes. Okay. Now, coming to security in Linux, this also we have briefly mentioned earlier, that there are separate bits mentioned to specify the protection mode of a file, because there are 3 groups of users we mentioned: owner, group and others. So, when an user account is created, your account will be created, you will be assigned to one of the groups, and others means everybody. So, there are 9 bits. The first 3 bits indicate owner, next 3 bit group, last 3 bit all others. There is 1 bit for every this group, and in the order read, write, execute, RWX. If it specifies like this, RWX, others are no access, I write it as 111.000.000. This means owner will have read, write, execute access, but group, other members of the group or anyone else will not have any access. But if I write RWX, then owner as well as the group will have access, that means 111.111. But if I write like this, read, write, dash, I do not have execute access, only read, write and read. So, the owner can do read and write, group can do only read. The last one here again, the owner can do read, write, group can read, anyone else can read. Similarly, I can specify any combination by maintaining or manipulating these bits. And for file protection, there are a number of system calls again available. You can also use some commands at the terminals, but these are some system calls available which you can call from a program, C program, let us say. You can change the mode of a file, chmod. See, same chmod command is also available on a terminal. You can also type, you can change the mode of a file. the access permissions. So, you can specify the path of the file and the mode, access mode, like that, whatever I mentioned 10000 like that mode you can specify. Similarly, you can check what is the current access of a file. Check access using the real UID and group ID, GID. Similarly, you can get UID, you can get effective UID. Effective UID means sometimes what happens, you can log into a system and while you are logged in, you can re-log in as another user. That will be your effective user ID. Okay. So, but your original UID is also remembered. Similarly, you can have a group ID, get group ID or get effective group ID. You can change the owner of a file, specify the path of a file, specify the owner and specify also the group, what will be the group of the file. So, you can do this provided you have access. Normally, the super user or the root privilege users will be allowed to do this for any file, or you can change the UID or the group ID of a file. You can also change these things. So, over this course we have tried to discuss all the basic elements of an operating system, what are the different components of an operating system, how they work, how they interact with each other, and I believe with this basic background you will be in a position to explore the topics further, because as I said in this last module under Linux, I have only mentioned the things very briefly and sketchily. There are detailed documentation and books available on all these topics. So, if you are keen to dig into systems engineering, learn about these operating systems, how they work, you will have to devote time and effort to understand the exact mechanism of a real operating system, how it works, and then of course, you will be able to do all these things. So, with this we come to the end of this lecture. Thank you again.